Welcome, everyone. On behalf of the Royal Aeronautical Society Stevenage branch and also Leonardo, welcome to our Luton site. It's good to see everyone's braved the weather to be here for such a great turnout. I'm going to hand you over quickly to Fiona Clark, who's going to introduce our speaker. Fiona is our Head of Capabilities for EW sensors here at our Leonardo site. So welcome to Fiona. Okay.
This will really worry Steve because I've got notes and he knows I never use notes, but I thought I didn't want to forget anything this evening. So hello, everybody. Welcome to the site. And it's lovely to see so many old friends as well. So welcome back. It's my great pleasure and honour to introduce our speaker tonight, Steve Roberts. Having been sponsored through Cambridge University by GC Marconi, Steve joined the company in 1979, where he quickly became known as an enthusiastic, super bright engineer with a passion for all things EW and a strange penchant for lumberjack shirts.
Which I'm still wearing.
Yeah. Steve spent over 20 years leading various engineering teams, including the Performance Assessment Group, who used simulation and modelling to design and prove the EW systems that went on to see active service for many decades. This team was a trailblazer for what we would now call model-based system engineering. I was lucky enough to join Steve's simulation team in 1986 as a shy young graduate, which is hard to believe, I know. Steve also led our trials teams and was responsible for many of the tactics and countermeasures that have been employed by the RAF on Harrier, Tornado and Typhoon aircraft to this day. Sadly, Steve was promoted, as all good engineers are, to Director of Technology, Director of Capability and Director of Strategy, taking the business through a number of significant changes. Along the way, he has been absolutely brilliant to any young person working with him, and he has brought many of those in this room along with him and shared all his skills and expertise with us. He's also been recognised by a number of prestigious institutions. Steve was appointed Visiting Professor of EW Systems at Cranfield University Defence Academy in 2011. The Association of Old Pros and Association of EW Professionals inducted him into their EW Technology Hall of Fame in 2014, and Steve currently serves as the president of the UK chapter of the AOC. He is especially proud of receiving the Silver Specialist Award from the RAeS in 2016 for his contribution to aircraft and aircrew survivability. Steve's passion for EW continues, and I know that he will present a fascinating look into the history of this black art this evening. So, ladies and gentlemen, please welcome my boss, my mentor and my friend, Professor Steve Roberts.
Thank you. Well, that almost makes me speechless, which is also unheard of. So I hope you'll be able to hear properly at the back. If you can't, sort of wave hands around. This room has been the scene of much bloodletting, shouting. This is where we saw our quarterly business reviews. So when I would present things like technology plans and strategy plans, the bosses would be all arrayed there and would shout at me and tell me I was talking rubbish, which I'd rather you didn't do today. So Fiona has, this is where you sort of hope the mouse thing's going to work, and it's not. Why not? Okay, we've gone shooting on.
It's a bit slow.
Bear with me for a moment. Why have we not connected correctly? So I was going to say the first thing was Fiona's actually mentioned quite a lot of this, my background. So realistically, I started doing real technical work, assessing quite a lot of things. We used to write a lot of models of things like Russian air defense systems, which is one of my big passions. Other passions are cars. You may wonder why all the cars have got little flags against them. Well, as we go through this, I'm going to introduce the story of EW and how it impinges on various nations through history. So the first thing to do is we need to look at what is electronic warfare. Well, it isn't electronic warfare anymore. It's now electromagnetic warfare. And it's basically the battle for the control of the electromagnetic spectrum. And all the various ways of showing it, this picture, which I nicked from a radio astronomer's one, is the one I like best because it kind of gives you an idea of wavelengths. So a sort of soccer field wavelength is associated with low frequency. As you move up in the frequency spectrum, so you move through the megahertz to the gigahertz, you start to come down to centimeters and millimetric And that's partly how radars are classified. So the things we're interested in this space, metric radars, centimetric, millimetric. So I'll keep mixing frequencies and wavelengths through this. I think I'm going to focus mainly on air. So let's look at an aircraft. You can see there's an aircraft there in the middle of the sort of dark, muggy skies. So what signatures might that aircraft have in the electromagnetic spectrum? Well, the first thing is if it switches on its navigation lights and you look out at the night sky, you'll see aircraft because they're lights. So that's invisible light. If they're chattering on the radio and you're listening on the right frequencies, you'll hear their radios. If they've got their radars on and you've got the kind of equipment that is made and designed at sites like this, then you'll be able to collect the signals from the radars and any data links in the microwave bands. And most aircraft as they fly will heat up a little bit, or the engines will be heating up, and that means there's infrared energy to be collected. And lastly, typically with guns and missiles, you'll get ultraviolet flashes. So collectively, all those parts of the spectrum result in something you can see and hear, either with your naked eye. I haven't covered acoustics, so it's not your ears, but electronic ears. The other thing you can do, and which we all do every day, is you can illuminate objects with electromagnetic energy. And the most obvious example of that is the sun, which is a big ball of electromagnetic energy illuminating everything so we can see things by the reflected light. But equally, we could see things that were reflected from searchlights or radars. So that's all I need to say about how the spectrum helps you see and hear and detect aircraft. But stealth is the opposite of that. So in a stealthy platforms like either the F117 or a B2 type platform, what you're going to try and do there is to reduce the signature. So you're going to try and reduce the energy that's produced by the heating, by the radars, by the radios. And the hardest thing to get rid of is the visible light reflection. But ultimately, if you go back to night again, you can't see them. So that's stealth. It's just removing all the things in the electromagnetic spectrum that would allow you to detect it. Now, there's a few slides with loads of words on. This one is important because every single acronym on there is part of the alphabet soup that we electronic warfare people create to mystify what we do. Basically, in amongst there is EW, which is now part of a wider thing called electromagnetic spectrum operations. And all those other acronyms in there are just things that we do in EW or we make in EW. What I'm going to come back to quite a lot tonight is these three things: electronic surveillance, which I'll abbreviate as ES, electronic defense, ED, electronic attack, EA. And these are the three facets of what AEW and EMSO makes up, really. You're going to try and listen or watch and see how your opponents or potential opponents are using the electromagnetic spectrum. So listening for them, what they do, collecting information. Once you've worked out what they're doing with their electromagnetic spectrum, you want to be able to stop them doing it. So defense is ways to protect your own assets from whatever they're doing. And lastly, obviously, attack is when you deliberately do something to mess them up. So I've got 150 years of history to cover in the remaining 54 minutes. So that doesn't give me many minutes per year. And if we invert that, it gives me quite a lot of years per minute. So we'll rattle through this. There's not going to be time to talk about anything in technical detail, but I want to talk mainly about radio and radar parts of the spectrum. I'm going to talk mainly about air operations. And I'm also going to tell you a little bit about the industrial history, because I think that might be of interest to some of you in the room. So we're going to start with the industrial bit and say aerospace starts in 1783 when the French do some stuff, quickly followed by the Scots. So in Britain, the Scots are the leaders on hot air. Balloons, sorry. And meanwhile, down here, there's a whole pile of guys playing around in electrical space. The first person to propose forms of telegraphy is actually a Spanish guy, Campillo, in 1804. And then it's gradually brought in by some Germans and some Brits and some Americans, so that by the sort of last part of the 19th century, there's a lot of companies operating in the electromagnetic, well, electronics, electrical telegraphy, beginnings of telephones by about 1876. But the EMS, the thing that actually would join electrical stuff to the stuff around us, the ether, nothing happens until Heinrich Hertz's experiments in this sort of period here. Now, Hertz proves Maxwell's theories about how electromagnetic waves interact and how they can move at the speed of light and things like that. But when asked what use are they, he said, I can't really see any use. They just, I think, will be a scientific curiosity. Marconi, who was half Italian, half British, thought there was something in it. He realized that if he could avoid the wires that were used in telegraphy, that he could create something that would allow you to transmit information through the ether over great distances without wires. Eventually, he proves that he can do this across the whole of the Atlantic, did it across the Bristol Channel first, so talking between Wales and England, another miracle. And he introduces what's known as wireless telegraphy or radio telegraphy, so RTWT. Only takes a matter of probably less than 5 years before radios are all over the place. And the first use of electronic warfare in a military context is in the siege of Port Arthur in 1904. The Japanese and the Russians have gone to war. The Russian Pacific Fleet is in Port Arthur. It's besieged by the Japanese. They're lobbing shells in to attack the ships. The Russian Admiral Makarov realizes that they're using radios to control the fall of shot. So when the gunfire goes in, they would watch for the splash. He gets people trained up to listen using the Russian radios to listen to the Japanese radios. And then he told his teams to hold their finger on the transmit key. So where you were using going did it with their radios, they would just go da, blotting out anything that the Japanese were doing. Despite that, all the Russian ships were either sunk, damaged, or scuttled, and the Russians were defeated in this sector. They decided they needed to send their Baltic fleet round, and they sent the Baltic fleet all the way around the world. And as it got close to Japan, in the Straits of Tsushima, between Korea and Japan, the Japanese were listening on the radios and they could hear the Russian chatter. They did a direction finding, so they got the angle to the Russian transmissions and they got their fleet out to ambush it. And the Russian whole Baltic fleet was devastated and destroyed. End of war. About 9 years later, there's another war. And in this case, Britain has watched this, and having got Marconi, and Marconi is buying up just about every European guy with any clever ideas, and he persuades the British government to start deploying bits of Marconi equipment. This is called a Bellini-Tosi DF receiver. It's actually also called a goniometer. There's a dart thing on the top. You connect that up to 4 antenna towers, and with the 4 antenna towers, each collecting signals, by adjusting the goniometer, you can find out the angle at which the radio signal is arriving. This guy, Reggie Hall, realized that tracking and finding these radio signals was going to be a great benefit. So they took over a load of radio stations, many of which were Marconi civil ones, which were then absorbed into the Admiralty's network, right the way down the east coast of Britain, all with telegraph lines back to a control centre in Whitehall called Room 40. And this allowed the British to track German warships, and more importantly for our air context, airships. And the Germans had a rather strange habit at this point of every time an airship took off, it had to say on Morse code by its radio, did, I have left my code books behind. There is no danger of anyone capturing them. For the rest of their mission, they used to send messages without any coding. And once an hour, each airship had to say, I think I'm here. And what the Germans would do was they would use their direction finding systems to work out where the airship was. They would send a message back to say, no, you're not where you thought you were, you're here. And that would get plotted, not thinking that the British were listening to all these transmissions and plotting them. And Marconi were plotting all these Zeppelin tracks from their bases over in the Low Countries as they came across the channel. Just purely by coincidence, this plot, which is another copy out here, is the night of the 27th, 28th of November. So this is actually what happened last night, 108 years ago. And late in the night, they picked up this one Zeppelin, which was coming in over towards the northeast coast here. They plotted where it was going to be. They sent this young pilot up in a BE-2C, which was a pretty cronky aircraft with just one little Lewis gun on board. He had to go up with no radio contact to the aircraft. He was told, go that away, you'll find an airship. And sure enough, he did, and it was shot down. And the same night, another one was shot down here by this same defense system. So by the end of the First World War, we've now got a lot of companies have started to pick up on this new EMS stuff, as well as the electrical telegraphy they were doing before. The aerospace world, there've been about 18 companies created making aircraft, and over the next 30 or so years, these companies gradually coalesced. The two biggest blocks were Vickers Armstrong and Hawker Siddeley, who kept actually making aircraft under their brand names, but they were single companies, and there were a few smaller companies. The other thing to notice is all these companies start to mix up electrical and EMS. So there's radios and other stuff coming along through here, and it's really electronics. And by the Second World War, the electronics have gone mad. And in the next 6 years, there's things of all flavors are created to do navigation, sensing, jamming, networks, communications. And it's described in British histories as a war in the ether. So this is the idea that electromagnetic signals are somehow carried by something, which was the ether, which was later, of course, proved to not really exist. Now, all of those are radio or radio frequency, except for this little one down here, which I won't talk about tonight, other than to say, if you're interested, go and look up Spanneranlage, which is an infrared searchlight and detector system, which the Germans tried on a number of their night fighters. But we're going to focus on radar. And of course, the main radar in the world, the first one ever, was the chain home system. It's not true, but it makes a good story, right? Britain was the first to deploy a network of radars to protect the nation. And this is chain home in its full configuration. So the chain home radio direction finding, the code name for it, 2 or 3 transmitter towers. On these, they had antennas that would transmit like this, and you could have multiple frequencies, and these are the 50 megahertz frequency towers. And in between the towers, they would hang an array of metal wires to make a big sort of curtain antenna, probably as big as this room, which would be used at the lower 20 megahertz frequency. You might wonder why there's a picture of Dover Castle. I was at school at Dover. I used to do dinghy sailing in the harbour, and I was terribly into fortifications. You may have seen that before. So I used to love looking at Roman stuff and Iron Age stuff and Saxon stuff. And I'm always a bit curious about what these were. And my dad, who was in this whole business, he was a British Army Royal Signals officer, as indeed was my grandfather and my great-grandfather before, although they were Royal Engineers. He told me what those were, and it started me thinking. So anyway, so these chain home, first 20 stations were deployed. They were out and in use during 1939. The receiver elements of it, which is these 4 towers here, which look very familiar to you because they're the same type of things as were used in the First World War. They were made by Cosser, and the engineer in charge of that was Leslie Bedford, which I'm not sure all of you would know. So that bit there is definitely a reminder of why we're here tonight. I was out at sea watching these things. Many years before I was there sailing, the Graf Zeppelin was sent on an electronic surveillance mission just before the Second World War. It trundled up and down the East Coast, kept hearing this sort of and just went, what on earth is that? What they were hearing was stuff at 25 pulses per second. So these radar transmitters were blasting out over a really wide pattern, 25 times a second, which isn't much. And it was a sort of low level bubble. You might wonder why 25. Well, they actually were relying on the British electrical mains system of 50 hertz, and they used the 50 hertz waveform on the main signal to control the pulsing. So every radar station was given a time on the 50 hertz cycle. And the Germans thought nobody would build a radar at that sort of frequency with as few pulses per second as that, and with pulse durations this long. They just thought this was bonkers. And so they said, this is not a radar. You do not need to worry. Britain does not have a radar. Only within the last few weeks, I've discovered that they were probably a week or two too early on their system, because the British started to deploy chain home low, which looks much more like a conventional radar with a dish that rotates. And between about August of 39 through to June of 1940, they deployed another 40 of these chain home lows. And if the Germans had heard those and detected those, they would have gone, those are radars. Why didn't they? Because the frequencies that chain home were using were very close to the frequencies the Germans were already planning to use for their bombing aids. So the first of these was a thing called Knickerbein, and that was deployed, 2 of these quite early on in the war, 2 beams produced by this massive thing with loads of dipole antennas on it, and this could be swung around on a turntable to create the 2 beam shapes. Each one of these produced 2 relatively small beams, and one of the beams went beep, 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 and the other one went beep, beep, beep. So if you flew into this beam with your receiver listening, if you were one side of it, you'd hear beep, 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 and if you're the other side of it, you'd hear beep, beep, beep. But if you were right in the middle, the 2 joined, and you heard beep. So the German bombers just had to fly into one beam, fly down it. When they heard the other beam, they pressed the bomb release button. So that was Knickerbein, which was fairly quickly discovered. We'll talk about that. And then they came up with 2 more versions, which just had more beams and more clever modulations. Problem was, people had been talking about it. German pilots were talking about it after they'd been captured. There were some intelligence reports. And R.V. Jones, another one of the sort of great heroes of this world, ran a small department that was so small it was him. And Winston Churchill and Lindemann had said, just do whatever you can to work out what they're doing with the science. He was given permission to take an Anson up with a radio receiver, and they quite quickly found the Knickerbein beams, found the tones. They realized that every night the beams would be on different frequencies and the tones would be slightly different. So one night it might be beep, next night it might be beep. And it was only any good to jam them if you could transmit a signal on exactly the right frequency with exactly the right tone. And these things were called aspirins, because these were called the headache flights, to go and listen to the thing that was causing them the headache. The aspirin jammers could be tuned up as soon as they'd found the signal for the night. They'd send a message. The aspirin jammers would be tuned up and just go beep, 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 very loudly. So wherever the German bombers were, they just heard beep, 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 beep. And then the 2 second systems were beaten by bromide, another kind of painkiller, and domino. And that's really, I think, why the Germans hadn't spotted what chain home was early on in the war, because they were really way ahead in this sort of technology. And their radars look much more like radars. And they deployed a surveillance radar called Freya, standard sort of mesh grid thing that rotated. You can see it's got a much higher frequency. It fires 500 pulses compared to the 20 odd. And they also had ones that look like these, which look like pretty ordinary radars to you, called Würzburg, and the bigger version, Giant Würzburg. And these were deployed in a thing called the Kammhuber line, or Kammhuber line. And the way it worked was a Freya would have under its command a few guns, a few searchlights, and a pair of Würzburgs. And when they found a bomber, they would pick one bomber. They would tell one of the Würzburgs to track the bomber. They would set the second Würzburg would track a night fighter, which was flying above a beacon. And then on the ground, they would issue commands to the night fighter to steer it towards the bomber. On the night fighter, there would be a small radar system, which they deployed by then. And the final part of the engagement would be by radar control and visual at the very end. They did add some other stuff. If you're really interested, go and look up a thing called Kleiner Heidelberg, which is a fascinating device. And the UK obtained technical details by listening through the sort of headache type flights or ferret flights. And in the Bruneval raid, they actually stole some parts of the Würzburg to work out the frequencies. As a result of that, they were able to get a lot of equipment built quite quickly. They could only get hold of some old aircraft to start with, so Bolt-and-Pull Defiance, a turret fighter that really didn't do a fantastic job, but they were able to put some, because it had power, they wanted to put an early jammer called Mandrel, which could jam Freya, just basically where Freya would be scanning, this thing would just go. So instead of the Freya actually detecting anything, there'd just be noise. They were then moved into bigger aircraft, so they got hold. Britain got hold of B-17s and B-24s, which had a lot of power on board. 100 Group was set up with its motto, confound and destroy. And gradually these aircraft were equipped with, I put 3 of them here, but they had about 10 or 15 different types of jammers. One to deal with Freya, another family to deal with Würzburgs, and a lot of radio jammers to try and blot out or confuse the communication with the night fighters. But in fact, the most successful of all the countermeasures was a thing called Window, nowadays known as chaff. Basically, Joan Curran, who was a physicist at TRE Great Malvern, was previously part of the British sort of defence research establishment, is now one of Kinetic's bases. She realised what could be done to the radars with just pieces of tinfoil. And so they started to cut out pieces of tinfoil that were about half a wavelength. So we'll look at that in a second. They could chuck out hundreds of strips of tinfoil and create an echo that was way bigger than any of the aircraft would have produced. So every night, bombers would fly along, dropping piles of tinfoil, which by the time it got to a Freya radar screen would look like this. So the whole radar screen was covered with loads of echoes, which were actually being produced by these piles of tinfoil. The Kamhuber line just fell to pieces. The idea that you had one radar to find something, another radar to track one thing, another radar to track another thing, plus jamming of all the radio thing, it just collapsed. But the Germans had actually already got one called Duppel that they tried themselves. So they kind of knew what might happen. They didn't realize how bad it was going to be, but they worked out that they could do different things. So they changed the frequencies of the radars. That meant that you had to change the size of the metal foil you were dropping, and you changed the jammer frequencies. And basically during the war, the cycle time of every response and counter was about 3 months or less. And we can see one example of this with the German night fighter radars, the Liechtenstein. You can see these arrays of dipole antennas, so 4 channels, which would allow them to go in azimuth and elevation. So from the nose of that night fighter, they would get a target return and they would know if it was off to the left or the right or up or down. And this was a very good radar system. Wavelengths of about 0.6 of a meter. Remember, Würzburg 0.5, Freya 1. So if you cut lengths of tinfoil between about 0.25 meter, size of a ruler, 50 centimeters, so a big ruler, these would completely blot it out. Again, Germans went, what can we do? They couldn't go up in frequency for reasons we'll see in a moment. So they came down, and you start to see night fighters deployed with these massive antenna arrays for the SN2 radar, which was now running much lower frequency, and therefore the wavelength was 3.7 meters. So to defeat that, they started to drop pieces of tinfoil that were nearly 2 meters long, called rope was the name for that. And meanwhile, British had been worried about this, so they started to deploy some very early radar warning receivers. This is Boozer, the antenna for Boozer. A lot of aircraft had this. It did work very well, but there were so many bombers in the sky and so many night fighters in the sky that when you switch Boozer on, it said there are night fighters around. No shit. Basically, it was too sensitive. So they just realized they needed a more selective thing. And the next point where we see Leslie Bedford appearing is as the design and charge of Monica, which is the tail warning radar, which was deployed on a lot of the British bombers from 1942. there's this little antenna down there. It worked really well, but because it's a radar, the Germans have been thinking, what would we do if one of these was there? And it took a bit of a while for the British to realize why losses had gone up so high. And the problem was that the Germans were deploying this thing called Flensburg. And this receiver, top secret report, it's no longer top secret, but you could find it on the web, is by mistake, this Junkers 88 landed at RAF Woodbridge in July 1944. The story, I think it's probably true, is that it thought it was approaching its home base. It was coming the wrong direction on its landing beacon. So they think it lost orientation and flew towards Britain down the beam rather than back towards Germany where it was supposed to be going. And you can imagine them getting out, looking forward to their morning sausages and whatever, and were met by British people offering them bacon and eggs. There was a moment of panic. They didn't quite manage to do any damage to the aircraft, so R.V. Jones's team went in. They found that there were 2 extra antennas out here, slightly angled out, and there were 2 on this wing, one slightly angled up and slightly down. So the normal radar array is here. And what these were is they were homing in on this. So they were tuned to receive Monica, and they would now give azimuth and elevation to Monica. So in fact, the night fighters were coming in with their radars off and just homing in on the Monica radar, coming in behind, switching the radar on only at the last few hundred meters to get range, and then would open fire. And there was a bit of a battle, but not with Bedford. Bedford and Jones agreed this was now a disaster, and so all Monicas were switched off. In fact, they were taken out the aircraft. So British, meanwhile, have been trying to get radars with more resolution. The answer is to go into the centimetric parts of the spectrum, and it's the magnetron, a GC invention from down near Wembley way, that with you Birmingham University people, and these magnetron devices were taken over to the States with a Tizard commission. Funnily enough, I used to work with Tizard's grandson when I was at Stanmore, Andrew Tizard. I don't know if any of you remember. So we used to have chats about this way back then. And the British deployed things at 3.3 gigahertz. The radar that they used for the night bombers was called H2S. The Americans, went up to 10 gigahertz, and that's called H2X. And as far as I can tell, that is where S-band and X-band comes from. And basically, it provided quite good imagery of the ground. This is at the D-Day landings. These are the ships coming in on the morning of D-Day. And the other thing that you could do with the magnetron type small wavelength is you could make small, very accurate radars to put on night fighters. So the Beaufighters and Mosquitoes, mainly also in 100 group, were sent out over Germany. They would have in their nose the AI Mark 8 S-band centimetric radar. That's on a Beaufighter. It's there on the Mosquito. They also had 2 radar homing systems called Serrate and Perfectos. Perfectos was a bit sneaky, actually, because Perfectos could also blip out something to trigger the IFF, so the identification friend or foe, on the German night fighters, and then get a response from that and home in on that. As a result of that, lots of German pilots switched off all their sort of navigation aids, and a lot of them would crash on landing. So you didn't have to shoot them all down. But the Germans were still shooting down bombers. They rescued a magnetron, worked out what it was, and actually realized that because the wavelength was much smaller, they could build much smaller radar warning and homing receivers. And this is Naxos. Naxos is 4 antennas. Actually, it was two spinning, and these spun on a motor. And as they went round, they produced blips, and these blips were where H2S or H2X type signals were received. And it was so small you could put it on a single-seater plane, so not a night fighter. This is the Messerschmitt 109. There's the Naxos up there, and these guys were just sent up a bit like pilots in the First World War. They were told there are bombers up there, and so they would take off at night, fly. They had no real night navigation systems or anything. They just had to follow bombers and then tune onto their beacon and come home. They also tried to build a centimetric radar, but didn't get there in time. So the other part of what was going on in the Second World War with the Germans, who technologically were doing a lot of clever things, was they realized that they were running out of pilots, they were running out of aircraft, they were trying to make things cheaper. They thought, well, actually, what happens if we use guided, unmanned, or uninhabited, as we should say today, devices? And they started to build a family of surface-to-air missiles. There are about 3 or 4 others that I haven't shown here. Rheintochter I've picked because it's the one that was probably closest to being a success. It was command-guided surface-to-air missile. That means someone on the ground looks up in the sky, sees a target, looks for a flare in the tail of this, fires it, and then flies it with a joystick. And you're basically looking at the flare in the back, and you're trying to bring the flare on your missile in line with the target in the sky. And if you keep that, it will hit, or the warhead can be detonated. They realized that at longer range, this technique was quite difficult. It was quite difficult to bring the missile and aircraft together. So they started playing around on Ensign with an infrared terminal homing. So in the nose of these, they were planning to put a little infrared camera so that they could look for heat from engines and the like. Neither of these were fully deployed, but the scientists were around, and you may know at the end of the Second World War, there was a mad, frantic rush to get German scientists, and the Americans and the Russians and the British to a lesser extent went crazy to catch and find guys and offer them lucrative contracts. And as a result of that, we see that the first Russian surface-to-air missile, S-25, and the first American one, Nike Ajax, look remarkably similar, actually probably based fairly heavily on the same design team. And if you look at Britain's first one, Ferry Stooge, at the Radlett Air Show of 1947, it looks remarkably like an Ensign. But these SAMs, as I'm going to call them, people, I think, probably thought they were a bit of a novelty. They weren't convinced by them. There was talk about doing things like putting nuclear warheads on them. So if a bomber formation came over, you didn't have to be too careful. You just lob the nuclear weapon up there. But the first time people began to take surface-to-air missiles seriously was when a U-2 was shot down over Russia in May 1960. It was shot down by the S-75 Divina, otherwise known as SA-2. Actually, the first ever Russian system I ever played with was this one. This is the Fan Song radar complex. It is a complex thing. It has multiple beams. They sort of flap around the sky like this. So they have one thin beam that scans backwards and forwards like this, and one that does this. So it can look at a volume of sky about 20 degrees by 20 degrees and look at multiple targets in there. And it can fire 2 of these missiles and control them in flight. Bang, that came down. Everyone was really upset. It got a huge diplomatic incident. Interestingly, although this SA-2 was deployed back at the end of the 1950s, they're still in service today. There's a number of countries still using them, just with lots of upgrades. Just before I leave this, I should say that's not actually the first shoot down. First shoot down was kept very quiet and happened on the 7th of October 1959, when a Chinese SA-2 shot down the predecessor of a U-2, which was an IB-57. And they claim that they shot down 4 more U-2s, but no one can prove that. So what we get to then is a sort of view that the bombers, and you remember the sort of maxim, the bomber must get through. The British V-bomber force was going to carry Britain's nuclear deterrent. There was a bit of a scramble to get something into the air. So the Vickers Valiant was designed fairly simply and cheaply to get something airborne. Then the Victor came along, and then the iconic Vulcan. In fact, Victors did last longer, but as tankers. We've got, I don't think any of them are here today, but Phil Davis, who I know very well, was one of the guys that used to fly these and was on the last Vulcans that were flying. Phil's position would be down here, which is down at the back here. They got no ejector seats. If it was shot down, they had to drop out the front wheel door. So they had to let the undercarriage down and then go out onto the undercarriage and drop out. So down here, they would be watching on a number of receivers. They could control a comms jammer, a couple of UHF jammers against these kind of things, surveillance radars, and 3 what we call red shrimps, which were aimed at this sort of system over here. And then there was also red steer was a tail warning radar, a bit like Monica. I must just say that one of my other great heroes is a guy called Jerry Steer. And Jerry Steer used to take Russian radars apart as part of his life. And Jerry worked with us for a while, and that is named after him. So Britain named its red steer jammer after Jerry Steer. And if you're still watching Russian radars, on the top of a lot of Russian ships is a thing called top steer, and that is also named after Jerry Steer. This thing, Blue Saga warning receiver, so that would be listening to tell you what was out there. That was replaced by the ARA 18228, which was designed and built at our Stanmore site before the company moved here in 2004. So with a bit of luck, I should be able to let you hear what an operator would hear if an SA3, so this is the S125, otherwise known in NATO terms, the SA3, and that's its low blow radar. So if you're listening on your 18228, you would hear something like this. So that's the surveillance radar scanning, and you're hearing its radar pattern coming over you. They're going to turn the radar around, pointed at you. That's the radar going up and down, flapping madly to catch you. It's now locked onto you, so that continuous tone tells you that radar is staring at you. And that kind of random chatter is the radar system talking to the missiles, telling them to go left, right, up, down. And when you don't hear anything more, the missile's either gone past or you've been blown up. So you had, and that's about the time of an engagement. So from the time that you first come across one of those, they slew round, lock onto you, fire the missile, and the missile gets to you. It was that whole sequence you just heard. Now this stuff was happening for real in Vietnam. And in Vietnam, the Americans were flying a lot of aircraft, not just B-52s, but a lot of ground attack aircraft. They'd lost 2,000 aircraft over this period of time. And guess what they were coming up against again? S-75 SA-2. Start of the war, every 10 missiles that were fired, usually one aircraft would come down. By the end of the war, it was 1 kill per 50 missiles. Why is that? Because basically, they remembered during the Second World War that you needed radar warning receivers and jammers. And a lot of these aircraft didn't have them to start with at that time. So they started to send a lot of aircraft out to listen for what frequencies the SA-2s were using. They were known as blackbirds. Some of them were called ferrets. Some were called, and the point about this story is that the operators of the blackbirds were nicknamed ravens or crows, and crows was the one that stuck. And so in 1964, all the EW specialists in the US Air Force said, we need to form some sort of body that will share EW knowledge. So they created a thing called the Association of Old Crows, AOC. That's the thing I'm currently president of in the UK. I would encourage you all to join. It's terribly cheap, and you get a really good little magazine, and there's lots of seminars and lecture type things you can get. They're mainly American focused, but they are still useful. Now, the lessons from Vietnam were taken to heart by the Israelis. And in 1967, when they thought they were about to be attacked by the Arab nations, they launched a surprise attack. They had a reasonable amount of air power. They got in very low, very fast, and they wiped out most of the air forces of the Arab countries. And as a result of that, captured the Sinai, West Bank, and Golan Heights, and all the stuff that's still causing problems today. 6 years later, the Arabs had been re-equipped with a lot of Russian equipment, and it was stuff we'd seen before, the 2s, the 3s. They had some new mobile anti-aircraft guns, ZSU-23-4, and most of these, the Americans were confident that the kit that had been supplied to Israel would work, but it came as a bit of a shock when a lot of Israeli aircraft were being shot down, and they were being shot down at an alarming rate. 1 kill per 6 missiles was from this thing, SA-6. Which, if you looked at the very first picture at the beginning in my introduction, you'll have seen Fiona and me and some other guys here sitting on some of these on one of the test ranges. But when it was realized what was going on in 1973, the Americans sent a team out to Sinai very quickly. They got out there, they got some missiles, they got some of the radar systems. They realized that this was a new type of weapon for the Russians. It was a continuous wave, semi-active missile. That means They illuminate the target with a radar signal, and the missile homes in on the echo. So there's no ground intervention. No one has to fly the missile. The missile flies itself. It's a quasi-autonomous system. New type of jammer was sent out within a matter of about 5 days. And by the end of the war, we were now at 1 kill per 33 missiles. You may notice it's the same ratio as the effectiveness against SA2. So sort of an 80% reduction in effectiveness is what you're aiming for. Now you sort of wonder why that was such a surprise, because Britain had been deploying a thing called Bloodhound, another one called Thunderbird, which was the Air Force and Army's surface-to-air missiles. They'd been deployed from the late 50s. They were semi-active, continuous wave seekers. And Britain had them the whole time. And everyone in Britain was sort of going, that wasn't a great surprise to you, really, was it? And the answer was yes. Notice Ferranti's name appears here, Marconi appears here. There's the mobile version, and there's the not so mobile version. And look who was in charge of the design of the Thunderbird, Seeker and the like, Leslie Bedford again. The Royal Navy had something which looked rather ugly. A sea slug is a kind of appropriate name. Most British, for some reason, British missiles tend to use solid state boosters wrapped around the outside of them at this time. You see all of these have got like firework rockets around the outside. And the first of the modern British missiles, I think, was this thing, Sea Dart. So when I started work at Stanmore, I first went there as a student, schoolboy in 73. And then I was sponsored student by them from 76 through to 79. And when I got there full time, my dad had left the army. My dad had been taken on by Marconi, and he was put onto torpedo guidance and simulation work. And his first boss was this lady called Peggy Hodges. When I arrived as a student, Peggy was still there, and she was my mentor for my first couple of years when I was doing torpedo simulations. And Peggy and Leslie Bedford, between them, probably did more to drive British seeker technology forward. This was the one they were working on when I got there. Sea Dart, again, semi-active CW. If we look at what had been going on in the industrial space in this time, we've now confused the issue because we've quite happily settled with electronics and aerospace stuff, but guided weapons have appeared. And are guided weapons electronics, or are guided weapons just aircraft without a pilot? And there's a number of people who say, no, they're something separate. They're guided weapons or complex weapons or whatever you want to call them. But you can see who sort of won the battle: Hawker Siddeley, Bristol, and this rather interesting company, English Electric. By the end of the Second World War, all of them are working on guided weapons. English Electric has done a rather interesting thing and has bought Marconi, and a bit later buys Elliott. So English Electric were the ones who were saying, what we need is a vertically integrated company that can do airframes, motors, seekers, radars, and we can sell complete integrated systems without anyone else taking any profit. No, sorry, for efficient design and production. And during this period, various governments intervene, and BAC, British Aircraft Corporation, is created by merging Vickers Armstrong Bristol English Electric's aircraft part. The other bit limps on for a bit and then is acquired by GEC, ultimately forming a composite GEC with GEC Marconi. That's the point that my dad and I both arrive in this company about the same time. And some years later, we get British Aerospace being formed. A lot of those mergers are sort of being driven partially by things like Labour governments. So you often see quite a lot of the changes in the industrial landscape happen in Labour governments. So I'm looking forward to another set coming up now. Now, Britain in the Wilson government of the mid-60s decided that we were going to buy American, and the Phantom aircraft had been produced as a multi-role aircraft that could do everything. And it was a very, very effective aircraft. So Britain decided not to buy the TSR-2, not to go ahead with buying American F-111s, and to cancel the P-1154 VTOL fighter, which was going to be a supersonic version of Harrier. And the British bought them, but said we must have our own engines, because Rolls-Royce said we need industrial capability in Britain, and we must have our own electronics because that's national security. So as a result of that, the radar in the nose became a collaboration between Westinghouse in America and Ferranti in Scotland. The Ferranti site in Scotland had been formed in 1943 to do gun sites, gyro gun sites for various kinds of fighters, whereas most of Ferranti's operations started in Manchester. And the collaboration between Westinghouse and Ferranti also looked after the American jamming pod that was on this and a number of other British aircraft. But the radar warning receiver in the tail is the 223, again, designed and built down at the Stanmore site. And I think we still looked after them after we moved here. And there was the 223 and 228, essentially the same electronics with just variants on displays. But more importantly for the Phantom, apart from the fact that everyone bought it, is by the end of the Vietnam War, and particularly some of the lessons that also came out during Yom Kippur, there was a realization that a specialist aircraft was needed to attack radar systems. So this was to do a job called SEAD, Suppression of Enemy Air Defenses. And the Wild Weasel has its own emitter location system and the Shrike anti-radar missile. It's doing a job which actually was done during the Second World War by RAF Typhoons in 1944, were equipped with a simple radar homing receiver, and they would bomb around over northern France, trying to shoot up Freyas and other things like that. Meanwhile, we've got the Harrier sitting alongside. Harrier this was just supposed to be a prototype, P1127 in Kestrel. When the 1154 was cancelled, Britain made Harrier GR1 and 3. Americans did AB-8A for their Marine Corps. This guy had a fairly standard British fit of a Marconi ARA radar warning receiver with chaff and flares. We later upgraded that to a digital thing called Sky Guardian 200. And the Sea Harrier was created with the Ferranti Blue Fox, later Blue Vixen radar. These are the ones that went off to the Falklands, along with a couple of Vulcans, which flew incredibly long-range missions called the Black Buck missions. They had their 18228, as you heard a bit before. Some of the ALQ-101 jammers that were normally used on Jaguars, there was a sort of emergency fit onto those, and they also put some Shrike anti-radiation missiles on the Vulcans. But most of the work was done by the Sea Harriers and the Harrier GR3s, neither of which had jammers. So just to show that Britain could do it as well, there was a conversation took place on the 6th of May at that Stanmore site, and my dad was responsible for putting a jammer together from the bits of we were doing for the Sky Shadow jammer, which we'll talk about in a moment. And this thing was called Blue Eric, nicknamed that. They made 9 of them in 3 weeks, sent them out down to the Falklands, where they would have done a wonderful job, except they were on board Atlantic Conveyor, which got sunk by Exocets. Okay, the later Harriers were upgraded, and they now have, the British ones have an integrated EW system. Again, I'll touch on that in a few slides. The other big development at the time was Tornado, and the Tornado aircraft was the primary one was an interdictor strike aircraft, IDS. This had on board the Marconi Sky Shadow, RHWR, chaff and flare dispensers, and some of them were equipped with the Alarm anti-radiation missile, BAE missile with a Marconi Seeker. And that was the standard fit. We'll see that being used on where it gets used in a moment. The Germans and Italians also had a specific SEAD aircraft called the ECR Tornado, and Britain made a fighter version where we stuck a radar in the nose called Fox Hunter. That was done originally on the Milton Keynes site of Marconi. They used the Sky Flash missile, again another BAE missile with a Marconi Seeker. And later on, some F3s had some extra EW modifications, including towed radar decoy, where you tow a jammer 100 meters or so behind you. Now, these were used as the primary strike aircraft during Gulf War by the RAF, but the war started with a massive amount of SEAD. The Americans had things like this EA-6B, which was a Navy one, or the EF-111, big standoff jammers. They just blotted out the radio frequency space, made it very hard for things to be found. They were lobbing in anti-radiation missiles, their own harms, and the British were lobbing in alarms. Special forces were dropped to blow up radars, and attack helicopters were sent in to shoot them down. All of this provided an ideal environment for stealth aircraft like the F-117 to be slipped in unnoticed and deliver precision weapons very accurately. British effort in the end went up to medium altitude using laser guided bombs. So a laser designator pointing at a target, and the bomb has a seeker in the front looking for the reflected laser energy. But more importantly, we had to protect the aircraft flying at higher altitudes from things like SA-8 and SA-2 again. And a lot of the lessons learned in what was a relatively short, quite costly air campaign were used in the Middle East and the Balkans, where mainly it was Tornadoes and Harriers. Now, what's going on in the industrial space at this time is that the GEC Marconi combine has started to buy up things like shipyards. So we've now got an electronics company buying up shipyards. British Aerospace has been created by bringing together all the aircraft companies. Over time, what we see happening is that people are beginning to think, and you can look at this, this is the sort of Tony Blair's government period is around here. There starts to be a lot of interest in getting Europeans involved. So these 4 British electronics companies all end up under the French banner. So Thomson CSF, which later becomes Thales or Thales, depending on whether you speak Greek or not. And Marconi, sitting here, has started to buy up American companies. And it's pulled in Ferranti and Plessy. So you've now got one big electronics company, one big aircraft company, and you're beginning to see a few consortia formed, like the Space Consortia, Astrium, Civil Aircraft Consortia, Airbus. These are all companies owned by multiple people. Marconi starts going, we need to be in on this. They start talking to Finmeccanica, who by now have bought Augusta Western Helicopter Company, and a thing called AMS is created. So AMS is a subsidiary of Finmeccanica in Italy and Marconi. But all of a sudden, BAE Systems say, we're going to buy Marconi. And so for a short period, we have one company in Britain, which is controlling everything in the aerospace and electronic space, apart from a bit of French stuff. And this is also the period for the Typhoon, multinational program creating very capable aircraft with its very powerful radar, an infrared search and track system, and a complicated electronic warfare fit. There have been upgrade programs to make variants, and there's also been, just recently, the Germans have started to produce a SEAD variant they call EK. It's an ECR version like Tornado had. And if we look at a typical Typhoon RAF one from underneath, you can start to look at them and see where there's loads of apertures, RF and electro-optic apertures for laser warning receivers, missile warning, radars, and various ESM and jammers out on the pods. And there are flare dispensers, which can also be used to drop decoys, jamming decoys. And that's the kind of underneath. In the nose, you've got the original Captor M-scan, very, very capable radar, but it is a radar, pure and simple, really. We've always thought there was something could be done to make the radar a very, very powerful jammer or receiver. And so the ECRS versions are now what are called E-scan, so they can electronically scan the beam extremely high speed, and they can change the way the system is working. And ECRS Mark II, as you've seen in the press, includes EW functions. But by now, the type of operations the British are involved in have changed quite dramatically, and the helicopters become the primary air asset that's being used in the operations in Iraq and Afghanistan. And it was a tough time, because the things they were encountering out there were not the radar-guided surface-to-air missiles that all of the investment had been going against. What was happening was a whole range of short-range, mainly infrared surface-to-air missiles, so things homing on the heat, probably only capable of going out 3 or 4 kilometers accurately, plus a lot of unguided rocketry was being used and a lot of heavy machine guns. And it meant that you needed to be looking for threats, not in the radar spectrum, but now in the infrared and ultraviolet spectrum. So there was a sudden great rush and flurry of activity to make a new family of infrared and UV systems, missile warning systems, laser warning receivers, ultimately hostile fire indicators, so things that could work out that guns were firing and actually classify what type of gun it was. And new kinds of countermeasures, improved flares, and jammers operating in the infrared spectrum, things that fired laser beams back at missiles to blind the front end of the missiles. And these systems were called defensive aid systems, DASs, and they go by various names. A lot of the ones that came out of this site here were on a family called HIDAS, goes on to be called CDAS and NDAS and various other names for it. It's also been sold to a number of export customers, mainly through the US export Apache programs. And this is the point where this diagram gets really complicated, because there's now a whole pile of refragmentation, because BAE Systems decide that actually they're being constrained. They can't deal with this site in the way they thought, because the government says you can't deal with the former Marconi companies in any way that you wouldn't deal with another company. And Marconi were told you must give open market prices to everyone and tell everyone what you're doing. BAE Systems said this is ridiculous, spoke to Finmeccanica then and BAE Systems did some deals. AMS sort of split, parts of it and parts of Finmeccanica joined to create a short-lived joint venture, which went by various names of Celex. BAE Systems continued with some of what had been AMS, so particularly some of the naval radars. Meanwhile, MBD, which we hadn't really mentioned previously, which was the French and British missile companies, got part of AMS, forming the tri-nation MBDA. A few years later, EADS has appeared on the scene with its German, Spanish, French bit. They give up their guided weapons, and a bit later, the Spanish tack their bit in, and you get MBDA. Down here, BAE Systems are buying ever larger chunks of America, and up here, the complex world of these joint ventures for Airbus and Astrium, and EADS was the name that existed for a while. And this was all getting too complicated. So they just said, oh, let's give it all up. And gradually, Astrium and Airbus were absorbed into EADS, who decided Airbus was a much better name. Oh, and by the way, along the way, created their own German electronics company again. So it all gets a bit fragmented. Meanwhile, the French are still doing their stuff down here. Okay. So it gets complicated, but it's not half as complicated as what's now happening in the space where there's a huge pile of networking going on. And everyone says, the answer is you've got to make everything talk to everything and share data, because if you can have information sharing to everybody, power to the edge was a phrase, then everyone will know what's happening. So this is like being in a business and being sent every single email that's being sent to every person. You certainly will know what everyone is doing, or you might just end up not knowing what anyone's doing. Shared situation awareness, that allows self-synchronization. You don't need any bosses anymore. You just all do what you know is right. That means things happen really quickly. And that means you've got information superiority and therefore operational advantage, so you do a lot better than anyone else. That's actually what the Americans had done in the first Gulf War and in some of the later operations. So it does work, but it does have a tendency for bosses to feel like they're being left out, and they try and get control back. I shouldn't have said that anyway. Right, so key to working in a networked environment like that is a network-enabled aircraft, like the F-35. British service known as the Lightning II. Its main driver, I think, was cost originally, but it was also every country was going to have a piece of the action. So you'll see most of the publicities about F-35 always say which bit is made in the country. So they're forever doing deals to let a country that buys F-35 have some of the business. More importantly, is it's a very, very integrated aircraft. I don't know if any of you worked on it. The interior sort of data management service is incredibly complicated. And although there is a recognizable array-based radar in the nose, and there's a massively complicated RF-EW subsystem, and there's also a very complicated EO/IR system called a distributed aperture system, i.e. a DAS, not a defensive aid system, a distributed aperture system. All of these are really transducers. They collect data from the electromagnetic spectrum, turn it into digits, and some massive great computer inside stirs it all up and creates answers. So it's a data fusion, data-driven architecture. Because Italy and Britain have got Typhoons and these, a key requirement is to make sure these things can talk together. So the combination of chattering away like that becomes really important. Now, to do the same thing for the future, Britain looked at F-35, So back in July in 2018, the combat air strategy was issued by Britain. I wrote parts of that with the SGN and various others. And it was about saying, does Britain just want loads more F-35s? Do we want more complex weapons? Do we want more autonomous vehicles? And do we need anything that's a manned platform? The answer was yes. Tempest program was announced in 2018, later converted to GCAP. Lots of people here probably actually involved in that. And what we were pitching in some of the brochure type material at the time was we were taking all the sensing capability that the companies in Britain had done in the radar space, all the attack capabilities, and all the protection capabilities, and say in the electromagnetic spectrum, whether you're doing surveillance or defense or attack, they should all be integrated. There should be an electromagnetic spectrum system. And that's currently integrated sensing and non-kinetic effects. If we look at what that means, it means multiple aircraft can talk, look at the same threat, work out where it is. They can do cooperative things, so they can both jam it and same frequencies, different angles, whatever. They can tell other people where it is so they can shoot at it. They can have other things with very powerful non-kinetic effectors. And you can also keep everyone engaged. So that's fantastic. And when you look at that, it's a microcosm of this. It's just this tactical part of the bigger picture. So everyone is chattering, but what are they chattering on? They're chattering in the ether electromagnetic spectrum. So it doesn't take great brains. 12 years back, the Americans say, everything we're doing is really great, but there's cyber issues. So people can do network warfare, they can jam these data links, they can put the wrong information on the data links. And in fact, electromagnetic spectrum operations are at risk from cyber, which of course is brand new, except it isn't. Because if I take the history of electronic warfare and information warfare back to the beginning, I would say it starts back here in 1861. So I've just jumped us back another 35, 40 years, because telegraphy is critical to the Union forces' way of working and operating during the American Civil War. The Union has deployed a massive telegraph network all over the northern states, and they are utterly reliant on tap, 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 sending people to places. In fact, President Lincoln had a war room in the White House where every command was brought for him to see in the morning. He would get all the telegraph reports and try and control the war from the White House. Believe it or not. Confederates knew this, so the first thing they would do is anytime they found a wire, the first thing they would do is cut it. So people were denied information. So denial of service attack, like you sometimes see on the internet, best way you can do it with telegraphs is cut the wire. Then they get sneaky because they start listening. So they start listening to traffic, writing down, oh, so the Union forces have just been sent here. Well, we'll send some of our people there. Then they got even sneakier and they sort of cut the wires and put their own man in the middle who would listen to what the Union command was and then go, well, I'll actually send them somewhere else, and go tap, 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 and send them. And if you look through the history of the American Civil War, Union forces keep being in the wrong place at the right time. So in fact, we've got a whole pile of cyber attacks on a network. And I'm sorry to say that my very opening gambit about the first electronic warfare is 1904 in the Russian-Japanese War. It's not. In 1899, Marconi gets a contract to transmit the racing news on the America's Cup, which is going on. And they were transmitting news like the British boat is ahead, did-it-did-da-da-da. And all the gamblers would go, quick, change our bets, did-it-did-da-da. So in fact, the first radio communication is all about gambling syndicates, right? Betfred and all these things were in there back then. Marconi then goes, well, there's lots of other people like gambling. How about doing something with the stock markets? So he starts a transatlantic radio news and business service, tappy tap tap, you know, sort of General Electric shares up 1 penny, well, 1 cent, da, 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 da. And it doesn't take long for his rivals to realize that if they intercept these messages, decode them and get them to London faster, their brokers can make money. And so for a short period, Marconi's own messages are being stolen, and some are being corrupted, and passed to some of the brokers, and some were being passed a little bit quicker. And then because it was all about sport, that same company realized that the next America's Cup, every time the Marconi messages were going back, British boat just passing first windward marker, they would turn their radios on the same frequency and go and jam Marconi's signals. They said it was a code they'd invented. They said, instead of using Morse code, we've got a code which, instead of just having dit dit da da dit dit, we have dit 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 da. And they said, and if you hear did it da, it means the British are ahead. And if you hear da did it, it means the Americans are ahead, which was, of course, bollocks. They were just jamming. So, in fact, what you see is it's all about money. And if we extract, push this forward to the thing we're all talking about today, which is autonomous or semi-autonomous drones, UAVs, UAS, RPAS, whatever you want. The big guys are sitting here with these bigger aircraft and operators sitting remotely. The whole thing is dependent on the EMS. The navigation systems can be jammed. They can be destroyed. Chinese satellites up there destroying other satellites. For what purpose? The communication is easy to intercept, jam, denial of service, if you know where it is. And the trouble is these things are chattering away all the time. So if you've got the right receivers, you can hear them. And if you go on the internet and go how to kill UAVs, you'll find complete step-by-step instructions as to how to make jammers against GPS. You can build one that's probably not much bigger than a mobile phone and probably blot out GPS signals or GNSS signals for about 2 miles. Ukraine has shown how valuable these are, but also how vulnerable. The response times are now similar to those in World War II. Every time a new drone type function appears, about 3 to 6 weeks later, the other side have overcome it. But 3 to 6 weeks later, the other side have overcome whatever it was you did to overcome them. So this is just the same cycle of capability now going on in the cyberspace. And I've been banging on for a while that we've still got a bit of a recession with protecting platforms rather than information and bandwidth. So I've taken, 9 minutes longer than I was supposed to have done, which I think is not bad to take you through 150 years of history. Nothing's really changing. What's going on today is the same as was going on back in the 1850s, 1860s. It's just the medium slightly changes, the frequencies change, the types of patterns of pulses and so on change. So we've seen a battle going through the radios of the time, then radars. Then we saw people using these things and trying out new ideas in the proxy wars. We got a bit of a shock when the Balkans and Middle East happened and we met things we weren't expecting because we hadn't thought ahead about what might happen. And we're back into a new cycle. The argument is you should always be thinking about what might happen. Anything you build, I would always try and find a way of breaking it. So I was notorious in the labs here, but the QA people on site here used to take me down the labs and say, can you break this? And if I couldn't break it, and I wasn't allowed to use a hammer, but I mean electronically break it. So this was what my message would be, is always think ahead. I think I've tried to tell you a little bit about the parallel story about, because there's money in the electromagnetic spectrum, there will always be a battle for who's working in it. And I've told you, we've still got to do surveillance, we've still got to do defense, we've still got to do attack, but we've got to do protection of information and bandwidth. And that is it. So I hope you found that of interest. We've got, I guess, I was told you wouldn't have to finish till 8. So I've got about 10 or 15 minutes of questions, if anyone would like to ask anything.
I was going to say thank you on behalf of the society and everyone joining. So as Fiona said, the food is warm, so we'll finish there. Any questions, obviously, we'll have a bit of a networking session afterwards, so it'll be great to come and ask all your questions to Steve. But I just want to say a massive thank you to you. To everyone who kind of helped us today. There's a lot behind the scenes setting up. I think it worked really well. So, and everyone for joining as well. Thank you for coming. But a massive round of applause for Steve, everyone.